Hello and welcome to this video tutorial. Today I'm going to demonstrate how to convert a tin elevation dataset to an elevation raster using ArcGIS and the 3D Analyst extension. Some background information before we get started. Different GIS packages and CAD packages often have their own formats for tin data. This can be troublesome because if you want to use an elevation dataset between multiple packages, you often have to convert it from one format to another. Tin data in ESRI is stored as either a coverage file or a terrain dataset. Both of these files are proprietary ESRI formats, so there is limited support for them in other mapping packages. Raster elevation datasets, on the other hand, are widely supported in different GIS packages. There are a number of very common formats, including TIFF images, ERDAS imagine files, and ESRI binary grids. And these datasets, they're very simple for these packages to draw. They don't take a lot of time. They're fairly portable, and there often aren't any limitations on how these files can be used. They can often be used in the same ways that a tin file would be used. So in this tutorial, I'm going to show you how to convert a coverage tin, so a tin that is stored within an ESRI coverage file. I'm going to show you how to convert from this to an ERDAS imagine image. Now, this process will work for other raster formats such as TIFFs, grids, bill images, etc. One thing that is important to note is that we don't want to use a raster format that uses compression, such as JPEGs, ECW files, etc. The reason is that for a raster elevation dataset to be of any use, the precise elevation values are stored in the image, and using a compressed image format destroys these elevation values. It can still be used as a background image, but you can't interrogate the specific pixel values or perform other GIS operations. So be sure to use an uncompressed format. So first what we want to do is set up ArcCatalog so that we have the necessary tools available. So first up, we're going to disable background geoprocessing. Now, the reason we're doing this is that background geoprocessing works just fine, but it gives you less diagnostic information. When you're running a tool, you'll see a blue progress bar at the bottom of the page, but it can be hard to tell exactly what's going on and what progress the tool is at. To disable this feature, we're going to go up to Geoprocessing and Geoprocessing Options, and we will uncheck this box here that says Background Geoprocessing. And what this will do is when we run the tool, we'll be presented with a dialog which has more diagnostic information. So this can be helpful if there are any errors or if we need to troubleshoot anything. Next up, we're going to enable the 3D Analyst extension. This extension gives ArcGIS image processing capabilities. So to do that, we'll go up to Customize and Extensions, and we'll check the box next to 3D Analyst. Now you won't see any changes here, but what it will do is it will enable a number of toolboxes for image and 3D processing. So before we convert this tin to a raster, It's important to check the integrity of the file. We want to make sure first that the file is complete, that there aren't any glitches or other errors. We also need to note down a few pieces of information which will be used later on in the process. So first up, we're going to right-click on our tin and select Properties. And we'll have a look at the XY coordinate system. Now in here we can see that the data is stored in NAD 1983, State Plane, Arizona, Central FIPS 0202 International Feet. So this is using the North American datum with the Arizona State Plane projection, and all of the tin data is stored in international feet, which you can see here, foot 0.3048. During our processing later on, when we're asked to enter distances, cell sizes and things like that, we'll be entering those details in international feet. Let's have a look at the Z coordinate system. Now at the moment there is no coordinate system defined, so just by looking at this we can't tell how the elevation data is stored, whether it's stored in meters or feet or another unit. So to find out what system the elevation data is stored in, we're going to have to compare the tin to another data set. So to do that, let's open the data up in Arcmap. And what I have here is the tin at the bottom and world elevation contours. This file is supplied by ESRI as a free dataset, and it contains large-scale contours covering the whole globe. So if we check this layer on, and this is going to take a little while to draw, so we'll go to Properties and disable the shaded areas. And that way Arcmap will only show the edge lines which have been used to create this data set. So those edge lines are drawing now, and once that's done, the contour layer will also be shown. Okay, that's finished drawing. We don't have too many contours in this area. This data is near Tucson, Arizona. We do have one contour line up the top here, so we can compare the tin data to the existing contours. So if I look at the properties for this contour line, we can see that it is 600 meters. And if I have a look at the properties for one of the tin edges, we can see that the elevation is 2055. Now, because 1 meter is roughly 3 feet, I can look at this and see that the contour data is in feet. Now that we know the Z coordinate system of the data, we can have a look and see if there are any other errors that need to be fixed. So I'm going to turn on the elevation fill. And already we can see a problem. As we saw before, the red edge lines, they only extend along here, but ArcGIS has interpolated this area in between. ArcGIS uses a convex hull when creating tin datasets. So what that means is any of these areas will be filled in. Now, this is a problem that needs to be fixed before we convert to a raster dataset, or else this area will be transferred across to the raster elevation. So what I'm going to do is open up the delineate tin data area tool. And what this does is it tells Arcmap what areas should be filled in, what areas should be interpolated, and which areas should be left out of the tin data. Now, this can be performed in either Arcmap or ArcCatalog. I'm going to use Arcmap so that we can see the results in real time. So open up the search dialog box and select tools and type in delineate tin data area, and as you can see, Arc has auto-completed, so we'll select that and click on the delineate tin data area label, which will open up the tool. So there are three options here. First is the input tin, which is the one we have on screen. So you can either click this browse button or click and drag across from the table of contents. Next up we have the maximum edge length. This sets the length of tin edges that Arcmap will exclude from interpolation. Tins are usually made up of small triangles, and the premise of this tool is that any tin triangle that has an extremely long edge is probably an error. There is no set rule for what value to enter in this box. It'll depend on the spacing of the tin edges, the quality of the input data, and things like that. So it might take a little bit of trial and error to get this right. First up, I'll try 100 feet and see what kind of result that produces. This last option here, the method, we'll leave as perimeter only. That is, we only want to remove interpolation on the edges of the data. If for example this data was over a large lake and Arcmap was filling in that lake as an error, we could set this to all instead of perimeter only, but we'll leave that as is. So click OK, and depending on the size of the dataset, this might take a little while to run. Okay, the delineate tin data area tool has completed, so I'll now click close and see what result we have. Now already this data is looking much better, but if you have a look in the northeast corner up here, you can see it's removed some legitimate data. So if I zoom in on that area, we can see that these edge polygons must have had an edge longer than 100 feet. So Arcmap has gone and removed those areas from the data. To me, it looks like we've run this tool with too small a maximum edge length, so we'll try and run it again. The delineate tin data area tool overwrites the tin file each time it is run. So each time we run it, it will remove the effects of the previous time it was run. So we don't need to run it on a fresh copy of the dataset, we can just run it again on the same tin file. So I'm going to open the tool up drag our tin file in. And this time for the maximum edge length, I'm going to set this to 1000 for 1000 feet. And we click OK. And again, this will take a few minutes to run. Okay, the tool has finished running, and this time the results look much better. If I click close, well, you can see that this time it has not removed these legitimate areas. And if I zoom back out, we can see that it has removed most of the fill from this concave area. It has left some data in the corner here. The trouble with this tool is it can be a compromise as to what value you enter in that maximum length field. Too small will remove legitimate data. Too large will leave areas in that we want to remove. But on the whole, I'm quite happy with this, so I think we'll go ahead and use this data as it is. So now that we have our tin file ready to convert, we're going to go ahead and open up the tin to raster tool. So in our search box, which is still open here, we'll delete the previous search and enter tin to raster and select that from the drop down, and we'll open up this first entry here, tin to raster 3D analyst. So there are several fields here that need to be filled in. First is the input tin. For that, we will drag across our open tin file. The output raster. This is the output image that will be generated by this tool. Now, it's important here to specify a file extension. The file extension that you enter in this field will determine what format the raster file is saved as. So if we click browse, I'm going to name this file elevation.img, and that will save this file as an ERDAS Imagine image. The reason I'm using this file format is it's fairly robust. It's stored as one single file rather than a multitude of files and directories that you would have if you saved it as an ESRI grid. It also has very few file restrictions. I can give it any file name that I want. I don't have to restrict it to 13 characters like a grid. And the images can be practically unlimited in size, whereas, say, a TIFF image has a limit of 2 gigabytes. In the output data type, we want to leave this as float. A float or floating point image stores decimal information in the file. So rather than elevation data being truncated to, say, 10 feet, 11 feet, 12 feet, saving it as a float, you can have values in between. For example, 10.5 feet, 11.25 feet, etc. The method field determines how ArcGIS will interpolate the tin data for the raster image. There are two methods available, linear or natural neighbors. For now, I'm going to leave this as linear. And depending on the results you get, you might want to experiment with trying out natural neighbours. It can be a little bit of trial and error, but in this case I'm going to leave it as linear. The sampling distance sets the pixel size of the image. So from this drop down I'm going to select cell size and delete the value that it has automatically filled in and enter 10. So this will create a raster file with 10 foot by 10 foot pixels. If you entered 1, you would have 1 foot by 1 foot pixels, 100 feet by 100 feet, and so on. The Z factor field allows you to convert between different height units. For example, I know that this tin data is stored in feet. So if I wanted to save the raster data in meters instead of feet, I would change this from a 1 to 0.3048 because 1 foot is equal to 0.3048 meters. Now I want to keep this data in feet, so I'm going to change that back to a 1. Now that we have all of these fields entered, we can go ahead and click OK to run the tool. Depending on the size of the data, this could take several minutes. Okay, our tool has finished running, so let's go ahead and check the results. Now at the moment the tin is drawing over the top of the raster, so I'm going to uncheck the tin from the table of contents and see what we have. And it looks like we have a good result. Let's zoom out. Okay, we can see that the tin has been converted successfully to a raster. Now, even though this tool has run correctly, it's still a little bit hard to see what the results look like. Most of the raster is currently coloured a fairly consistent grey colour. So let's go ahead and change the symbology to give this image more contrast. So I'm going to right click on the elevation raster and select properties. And under the symbology tab, I'm going to change the color amp from this drop down here and select this one here, which has a wide variety of colors, so it should give a fairly large amount of contrast to the image. I'm going to check the use hillshade effect box, and what this will do is it'll give the image a 3D effect. It'll highlight one side of a mountain and give a shadow to the other side. These settings, they don't modify the elevation image that we've just created. They only change how it is displayed in Arcmap. So if we go ahead and close Arcmap after this, the image will be unmodified. So let's click OK, and we can see a lot more detail in this image now. You can make out a mountain in the middle, some drainage lines along here, and if we zoom in, we can see that this is quite detailed. We can make out different fields, roads, drainage lines, and other features. So in this tutorial I've shown you how to convert a tin dataset to an elevation raster. We've looked at a few considerations and pitfalls, and we've looked at how to modify the tin data so that only correct areas are included in the output dataset. Thanks for watching.